Hello class and welcome to today's lesson. We are going to continue our work with graphing trigonometric functions. We're going to be doing transformations of tangent today. So if you can print the handout, it would save you a lot of writing. And you also might want a ruler for drawing in the asymptotes today. And perhaps a second color. Sometimes a highlighter or a colored pen might be helpful today. All right. So before we get into the transformations of tangent, I want to review the basic tangent graph with you. So if we think back to the previous lesson, I showed you how to graph tangent, and we could, draw the unit circle and plot a bunch of points. But once you start to get familiar with tangent, I think what you're going to find you do is you realize that since tangent has a period of pi, which is different than the period for sine and cosine, it's just half. So the period is only pi for tangent. If you remember that it kind of reminds us of y equals x cubed because of the concavity and the y-intercept is 0, 0, and it goes up to the right and down to the left. What I do is I say, okay, the y-intercept is 0, 0, I recall that. And if the period is pi, if that first full period of tangent is centered at the origin, then the first vertical asymptote must be half a period to the right. So if we go half a period to the right, that's pi over 2. And then if we go half a period to the left, that's negative pi over 2. So that distance is half a period. And that's your first set of asymptotes. So for your basic tangent graph, if you kind of memorize or realize that your first set of asymptotes are pi over 2 to the right and pi over 2 to the left, that makes a distance of pi, which is what the period is. And then the shape of the graph reminds me of x cubed. I'm going to go up to the right, concave up, down to the left, approaching the asymptote, concave down. And then I repeat the process. Since the period is pi, the next vertical asymptote will be pi units away, which puts it at 3 pi over 2. And I should be using a ruler here, and I'm sorry that I didn't. Halfway between those asymptotes, you're going to find an x-intercept. Then you're going to have a piece of the graph that goes concave up, approaching that asymptote to the right, concave down, descending toward that asymptote to the left. And you do want to make sure your graph actually approaches the asymptote. So sometimes when people do these graphs, they kind of just, they get a little sloppy with it. They just kind of like, whoop, I'm just going to go up like that. That's not what you want. You want to approach the asymptote. Now, we're skipping plotting all those intermediate points. We're skipping even plotting like pi over 4 and 3 pi over 4. But this is accurate enough. So it's not a highly accurate graph. We're not going to do a big table every time. But we do want to approach the asymptote. We want to put the arrows on the ends of the tangent graph. I don't care if you put arrows on the asymptotes, but I do want the arrows on the ends of the tangent graph because we want to remember the range for this is all real numbers. Goes up forever, goes down forever. Every full period achieves the range of all real numbers. So let's see, one tick mark away was of asymptote, so the next tick mark will be intercept. And to keep this pattern going, this one must be concave down, coming down toward that vertical asymptote. If we want to fill in the part of the graph to the left, if we are at negative pi over 2, we want to go to negative 3 pi over 2 for that next vertical asymptote. Halfway between the asymptotes, you're going to have an x-intercept. And then you can fill in the shape, approach those asymptotes. My steepness may not be very accurate. If I wanted to be more accurate, we could pick x's and find y's, but I don't think anybody wants to do that. So this sketch is probably good enough. And then at negative 2 pi, I'll have an x-intercept and a piece that goes up to the right. So that's how I usually graph my tangent graph. I don't really usually draw a unit circle and do the points. I just kind of remember that the period is pi. So the first set of asymptotes are half a period to the right and half a period to the left. And that first piece reminds me of x cubed. And that's how I graph tangent usually. Okay, so there's a quick recap of our tangent graph. Good news for the transformations. They work the same way as always. The one thing that's going to be different here is the period. The new period for tangent will be pi over absolute value of b. For sine and cosine, it's 2 pi over b. But for tangent, it's pi over b, or absolute value b technically. A still controls vertical stretches and shrinks. It doesn't affect amplitude because this graph doesn't have amplitude, but it will make it steeper or less steep. If A is negative, then there's been a reflection over the x-axis. B controls the period, which controls the horizontal stretches and shrinks. And B also can cause a reflection over the y-axis, which we won't do much of. We'll bring that up again later. C is your horizontal shifts, and D is your vertical shifts, just like normal. So let's go ahead and get started with our transformations. So here's our first example. I gave you a basic tangent graph underneath that we can maneuver and shift around, because for this right here, this is going to be a vertical shift up 2. I know it's a vertical shift and not a horizontal shift, because when you have y equals tan x plus 2, that's the same thing as just saying that the x is in parentheses. So if no parentheses are shown, only the x is inside of the tangent function. If I wanted to represent a horizontal shift, I would have to have parentheses around that entire expression. So this would be a horizontal shift, but this one here is a vertical shift. And that should look the same, similar to the sine and cosine. We know about those parentheses from the sine and cosine graphs. So we're going to do a vertical shift up 2 of tangent. So when you look at this graph, I want you to look and think about the asymptotes first. That's what I always start with, the asymptotes. If I move this entire graph up 2, will the asymptotes change or stay the same? They're going to stay the same, because if you pick up this vertical line and move it up 2, it's going to stay in the same spot. If I pick up this vertical line and move it up 2, it's going to stay in the same spot. So what I would do is grab a different color, because if you did print this, your pencil might not show up too great over the blue ink. And I would trace over those vertical asymptotes to start. I always start with the asymptotes. I've said that a couple times, so you might want to write that down. Just advice. And then what we want to do is take that tangent graph and move everybody up 2. So I take this x-intercept, I move it up 2, and then I try to maintain the same steepness as I go up to the right, approaching the asymptote, put the arrow on top, and come down toward the left, approaching the asymptote, put the arrow on the bottom. And I'm going to do that with each piece. So this piece, this x-intercept, is going to move up 2. It's no longer an x-intercept, this one. This one stayed a y-intercept. This one's no longer an x-intercept, but it's still a point of inflection. Because to the right, we're going to be concave up, try to maintain the same steepness, approach that asymptote, put the arrow on the top, and then come down toward the left, try to maintain the same steepness, approach the asymptote, put the arrow on there. I'm going to pause the video for you. Go ahead and finish that graph. Okay, so here's what my final graph looks like. Be very careful on the ends, because on the ends, it's easy to forget to do this part or to make it face the wrong way. So you do want a point here at 2 pi 2. It's going to be concave down approaching that asymptote. And this point's at negative 2 pi 2. It's going to be concave up approaching the asymptote. Notice, if you want to write this down, you can, but just observe that the vertical asymptotes, the domain, the range, and the shape of the graph have all remained the same. So when we did that vertical shift, those asymptotes and all these characteristics stay the same, but the x-intercepts are all different now. I don't know what they are exactly, but they're not the same as they were. It's just something to observe. And one more thing, just check your graph. As you did this, just make sure, once again, oops, I shouldn't have put that point there. Okay, when I move that up 2, you don't want to just do this. That's not what the graph looks like. Don't just drop down. Really approach the asymptote. And another thing you don't want to do is, even if you're good in approaching the asymptotes, don't stop your graph here, please. Continue that down to fill the viewing window before you draw that arrow. And I've tried to do that here to model what I'm looking for from you. Right, so that's a vertical shift. I trust that you could move the tangent graph up 3 if I asked you, or down 1 if I asked you to do so. And we'll get more practice with that in the days ahead. But let's continue on now to some horizontal shifts. So up next, we are going to take the tangent graph and we're going to move it right pi over 4. So again, I always like to start with the asymptotes. So when you look at those asymptotes, if you were to take this entire graph and give it a shove, so I'm going to take the entire graph and shove it pi over 4 to the right, are the asymptotes going to move or stay the same? They're going to move along with the graph. So what we want to do is we want to start by taking all these asymptotes and moving them pi over 4 to the right. So each tick mark is pi over 2. So we want to go half a tick mark. Okay, so this one's going to go half a tick mark to the right. Grab a ruler or straight edge if you want. This asymptote is going to go half a tick mark to the right. And I'm going to do all my asymptotes to start. That's my style. If you'd prefer to start filling in the full periods of the graph, you can. But my style is to do the asymptotes first. So I moved each asymptote pi over 4 to the right. Now, if you can focus on the asymptotes, which might be hard to do because there's so many dashed lines on this graph, as well as the regular tangent graph underneath. But if you can focus on my red ones here, halfway between those, there needs to be an x-intercept. So if you look, if you take that x-intercept and go halfway between 0 and pi over 2, that's halfway between those two red asymptotes. And then try to maintain the same steepness as you go up to the right and down to the left. And go ahead and repeat that process to fill the viewing window. Don't forget to do the ends. When you get to the ends, you won't be able to fit an entire full period. So like over here on the left, when you go to fill this one in, you're just going to have to chop off at some point, just truncate that graph because you won't be able to make it to another asymptote. So take a moment. I'll pause the video for you. You fill in the rest of the graph and continue when ready. Okay, that's what my graph looks like. And you can see I truncated on this end and this end. I didn't make it up to an x-intercept, so I just did my best to estimate. It is just an estimate. But if you look at the blue graph, it does look like I took it and give it a shove pi over 4 to the right. So it looks kind of neat. For the vertical asymptotes, those changed. So let's take a moment and use the shortcut notation to find out where they are. So the first one I notice is this one here, which is negative pi over 4. Because this would be negative pi over 2. And this is halfway between. So that's negative pi over 4. And then the distance between consecutive asymptotes is pi. Because for tangent, the asymptotes are always a full period apart. Feel free to write that down if you like. For tangent, the asymptotes are always a full period apart. And that's where my vertical asymptotes are. And I chose to use negative pi over 4. If you wanted to use this one, it would be 3 pi over 4. So if anyone has 3 pi over 4 here instead, that's absolutely fine. But the big deal with horizontal shifts is the asymptotes do change. So you might want to write that down as well. Vertical asymptotes are moved or affected or change when you have a horizontal shift. Okay. Next practice problem. Okay. For number 3, what I'd like us to do is graph negative tangent x. That's going to be a reflection over the x-axis. And if you notice, I changed the graph paper on you. I'm not sure which one you're going to like better. I think you might end up just liking plain graph paper better because I started you off with the basic tangent graph underneath, but it gets kind of hard to look at because there's so many lines and curves on that graph that I think you pick up things so quickly, you might be comfortable just go ahead and graph negative tangent at this point. I'll put up some graph paper for you so that you can print whatever type you like. But if you have a strong preference for one or the other, but I thought I'd just have you try some different graph paper for the next one. So this is a reflection over the x-axis. If you want to draw in your original tangent graph, you can. If you want to skip drawing in the original one, you can, and you want to go straight to the final. That's okay with me also. But what's going to happen here is if you think about or look at your original tangent graph, and here I'm just going to draw one piece. What's going to happen when you reflect over the x-axis is these asymptotes aren't going to change. Because if you take that vertical line, that is that vertical asymptote here, and you flip it over the x-axis, it's going to stay right where it is. So the asymptotes do not change when you flip over the x-axis. The intercepts don't change when you flip over the x-axis. All that's going to change is instead of going concave up to the right toward that asymptote, you're going to go concave up toward the left toward that asymptote. So I should have looked at it this way, actually. So this piece flips up. This piece flips down. And then over here, instead of going up to the right, you're going to go down to the right. And instead of coming down to the left, you're going to go up to the left. So if you can draw that in, go ahead and finish the graph. And if anyone feels like they'd be more comfortable putting in the original first, then do that. No big deal. So whatever way you're more comfortable. Go ahead and fill that viewing window. I'll pause the video for you. Continue when ready. Okay. So here's our graph after we reflect over the x-axis. I did not draw on the original for this. One thing to note, since this was an odd function, remember tangent's odd, when you reflect over the y-axis, you actually get the same graph. So whether you reflect over the x-axis or the y-axis, if that's the only transformation you do, you get the same graph. Because if you think about those pieces that we flipped, here's the original. Just look at that one piece of the original. If you flip over the x-axis, this piece maps onto that part. But if you flip over the y-axis, this piece maps onto that. And that happens with all the different parts. So whether you reflect over the x-axis or the y-axis, you actually end up with the same graph. Interesting to note. Up next, for number 4, let's try 3 tangent x. That's going to be a vertical stretch, or a vertical stretch by 3 if you want to write that. Now, when we go to do our vertical stretches and shrinks of tangent, one thing I just need to make you aware of is the expectations will be different than they were with sine and cosine. Because when you had like sine and cosine graphs, if you had like a sine graph and you had a vertical stretch of 3, you could show that the vertical stretch was exactly 3 because you have amplitude to work with. And that would be different than if you had a vertical stretch that was only 2 because you had amplitude. So for sine and cosine, we can show the difference between something like 2 sine x and 3 sine x. But when it comes to tangent, since we don't have amplitude to work with, what we're going to do is we're going to go back to when we were graphing things like y equals x squared. So if you recall from back in chapter 1, when we would graph y equals x squared, if we wanted to graph, let's say, 3x squared, what we did back then, since we were just going to sketch anyway, is we would graph the original and then just show that the new one is steeper. So by showing it's steeper, we've shown there's a vertical stretch. So we're not showing it's by exactly 3. So if I were to graph 4x squared, it pretty much looks the same as my 3x squared. We know this one's steeper than 3x squared. But in terms of the sketch, we just want to show that it's steeper and I'm happy. All right. So if you wanted to show like 1/2 x squared, do you remember from chapter 1? Was this sufficient to show that vertical shrink? No, it wasn't, because we don't have the original to compare to. So if I throw in that original, then you can say, oh yeah, okay, that was a vertical shrink. So we didn't show it was exactly by 1/2. We just showed that it got less steep. Okay, so that's what we're going to do with tangent, is we're just going to show it gets steeper or less steep. Unlike sine and cosine, where it's pretty easy to show exactly. I forgot to write the 3 here. There we go. Where it's pretty easy to show the difference between 2 sine x and 3 sine x, let's say. Okay, so for 3 tan x, here's what we're going to do. We are going to take the tangent graph and stretch it. So when we stretch it with a vertical stretch, it's going to become steeper. So if you want to draw on the original, feel free. And it's not a bad idea, because when it comes to a vertical stretch, the vertical asymptotes are not impacted. They don't change. Okay, because if you think about it for a second, if you think about like y equals tan x, there's a vertical asymptote at x equals pi over 2, right? Because if you plug in pi over 2, this is undefined. Well, if you plug pi over 2 in here, what's tangent of pi over 2? That's undefined. What's 3 times undefined? It's still undefined. So vertical asymptotes are not impacted by vertical stretches and shrinks. So the graph will get steeper, but it'll be steeper within the same bounds of those asymptotes. So asymptotes are going to stay in the same spot. Use that ruler, or you can use a note card or any straight edge if you're having trouble making those lines look vertical. And the x-intercepts are going to stay the same as well. Because again, think about basic tangent graph. There's an x-intercept, for example, at x equals 0. Because if you plug 0 in here, you get 0. If you plug 0 in here, the tangent of 0 will still be 0. And 3 times 0 is 0. So the vertical asymptotes don't change, neither do those x-intercepts. Okay, so what's going to happen is, if my usual tangent graph, let me just kind of sketch one in there, looks like this. When you go to do the vertical stretch, it's going to be steeper. So from here, it's going to go up faster. It's still going to approach the asymptote, but it's going to go up faster. It can be hard to make it look like it's approaching the asymptote because it is steeper, so it's hard to get close to the asymptote, but do your best with it. I just made that a little messy. Oh well. All right, so instead of coming down like this, we're going to go down, still concave down here. It's going to approach the asymptote, but it is steeper than before. So it's almost like you took that graph and you pulled it away from the x-axis. Do you see me vertically stretching it? So picture me taking taking the gray graph and stretching it vertically. It pulls away from the x-axis. And that's what it should look like. And depending on how steep you make it, it almost looks linear sometimes. So just be aware of that. It's kind of a tough thing to draw. So go ahead and fill in the rest of the viewing window. I'll pause the video, continue when ready. Okay, that's what my graph looks like for 3 tan x. However, this is not sufficient for my final graph because I did make the graph steeper. But do you remember that discussion about x squared, the stretches and shrinks with x squared? I couldn't just draw my final graph, because if I just draw this, guys, is that x squared, or is that a stretch of x squared, or a vertical shrink of x squared? You don't know because you don't have something to compare it to. So like if I were to put this in, if this is the original, oh, that's a vertical stretch. Maybe it's 2x squared or 3x squared. So just like when we did x squared graphs, I had to see the original to be able to tell that we did a vertical stretch or shrink. Same deal with tangent. So in order to show that this graph actually is steeper than the original, here's what I need. I need at least one full period of the original underneath. So you don't have, ooh, this one doesn't look very good. This one's pretty. I'm going to fix that. It looked too linear. I said sometimes they're tough. They kind of end up looking linear when they get steeper, but there should be some concavity there. So let me just fix that one up a little bit. That looks a little better. Yeah, okay. So there, that looks a little better now that I used the white out. Okay, so just show me one full period underneath so I can compare. You don't need to do a full period you don't need to do that under every single piece of this. You're welcome to do so, but show me at least one full piece of the original steepness so that I can compare to the new one, and we're good. Okay? And if we were going to graph 4 tan x, I'd probably draw pretty much the same graph. If we were going to draw 2 tan x or 5 tan x, I'd probably draw pretty much the same graph. Technically, 5 tan x would be steeper than this one. And 10 tan x, 10 times the tangent of x, would be even steeper. But we're not going to be able to show the exact steepness. We just want to represent that the graph is steeper. Okay. Let's continue. Next, we want to do a vertical shrink. So we're going to graph 1/2 tan x, and that's going to be a vertical shrink. You can write by 1/2 if you want. If you want to write down that it's less steep, feel free. And I'll pause the video, and you can fill that in. Continue when you're ready. Okay, there's my 1/2 tan x graph. So here's my original. I made it dashed this time. You can see my original steepness for tangent, which is not perfect. It's not highly accurate. If we wanted to be more accurate, we could pick x's and find y's. Feel free to do so, but I'm not going to. And sketching is sufficient for this topic. So here's my original, and then here's my new steepness, and just make sure you fill that viewing window. All right, continuing on our way. Our last set of transformations are the horizontal stretches and shrinks. So if you printed the handout, you have that information here. If you didn't print the handout, if you want to, go through them first and then decide what you want to write down, feel free. But here's my process for graphing horizontal stretches and shrinks of tangent. Okay. You can read that on your own. And let's go ahead and graph y equals tan 2x to begin. So the first thing I want to do is determine the new period. That's what the first step was. Okay, so the period for tangent is pi over the absolute value of b. So in this case, that's pi over 2. And then here's how I handle tangent. I handle tangent a little differently than sine and cosine because tangent has the asymptotes for me to work with. So the y-intercept is going to stay the same. That's like my anchor point. That's not going to move. What I do first is I calculate the location of the first set of vertical asymptotes. They're going to be half a period to the right and half a period to the left. So if the period is pi over 2, if I go half a period to the right, so half of pi over 2 is pi over 4. That's my first vertical asymptote. And then if I go half a period to the left, so half of pi over 2 is pi over 4. So I'm going to go that distance to the left. And negative pi over 4 is the location of my first vertical asymptote to the left. And the distance between these, if it's pi over 4 to the right, pi over 4 to the left, that makes 2 pi over 4, which is pi over 2. That's one full period. So once I have my first set of asymptotes, half a period to the left and half a period to the right, we can find all the rest of the asymptotes. So I'm going to go ahead and sneak one full period in here right now. So I'm just going to put one piece of tangent right there. And that's what it's going to look like, but we have to fill the viewing window. So we took tangent and we horizontally shrunk it. This is a horizontal shrink because the period got smaller. So, okay, so back to the instructions that I actually have here. Now that we determined the first location of the first set of vertical asymptotes, use the period to find the next ones. So if there's a vertical asymptote here at pi over 4, then pi over 2 away, there should be another vertical asymptote. So this distance is pi over 4, and if I get to here, it's another pi over 4. So if I go pi over 2 to the right, that's actually going to put me at 3 pi over 4. And it's half a tick mark and half a tick mark. Because think about the distance on this graph paper. Let me slide up for a second so you can see it without the graph on it. On this graph paper, 1 tick mark is pi over 2. So half a tick mark is pi over 4. Another half of a tick mark is another pi over 4, which gets you to pi over 2. And you want these asymptotes to be the same distance. This should be uniform. So the distance here should be the same distance here. And then my next asymptote, I'm going to go half a tick mark to pi, another half a tick mark to here. And I don't have to label all of them with their equations. I just started out that way for you. And then I go another half tick mark and another half tick mark. There we go. And you can fill in all your asymptotes like that. And then halfway, so we're going to do the same thing out to the left in a moment. Halfway between the asymptotes, you're going to have an x-intercept. That's true every time. So halfway between those asymptotes, you have an x-intercept. And then just draw a full period of your tangent graph. So halfway between these asymptotes, I have an x-intercept. And I draw a full piece of the tangent graph. Make sure on the ends that you fill the viewing window. So here, I'm not going to get to another asymptote, but I can see that I'm half a tick mark away, that distance right here. This distance is a distance of pi over 4. So that's going to be an x-intercept. And to maintain the pattern, this piece must come down to the right. So I'll pause the video. You finish the graph. And there it is. So it looks like a whole bunch. Actually, when you look at it, how many full periods do you see? 8 full periods. So there's 7 that are fully connected and drawn, and then there's a half and a half, and that makes 8 full periods in this viewing window. Let's take a moment. Let's use the shortcut notation for the vertical asymptotes and the x-intercepts. My vertical asymptotes, the first one I notice is x equals pi over 4. You can certainly use negative pi over 4. You can use 3 pi over 4. And the vertical asymptotes are, for tangent, are always a full period apart. So in this case, it's going to be pi over 2n, where n is an integer. And the x-intercepts, the first one I notice is at 0, so I don't have to write 0 plus. If you notice pi over 2 first, that's fine. Negative pi over 2 pi, whatever you want there. And for tangent, the x-intercepts here, the points of inflection, are full period apart. So if you started with 0, you'd do 0 plus pi over 2n, but we don't have to write the 0 in there. So for x-intercepts, I can just write that. All right. One more example to go. Our final example for today is going to be use the same process. You can probably guess. We're going to do y equals tangent x over 2. So tangent x over 2 is the same thing as tangent 1/2 x. If we go to find the period of this function, it's going to end up being 2 pi, which is a horizontal stretch because the period got longer. The period for tangent's usually pi, and now it's 2 pi. And again, I don't treat this the same way I treat sine and cosine. I treat this a little differently. I follow these instructions. I find the new period. I use the y-intercept as my anchor point. And then I go half a period to the right for my first vertical asymptote and half a period to the left for my other vertical asymptote. And if I find those vertical asymptotes at negative pi and positive pi, the distance from negative pi to positive pi is 2 pi, which is 1 full period, exactly what I wanted. Because this distance is pi and this distance is pi, so that all together makes a distance of 2 pi. Go ahead and finish that graph. That's what you should have. How many full periods do you see in the viewing window? 2. You have 1 connected full period and then a half and a half, so that makes 2 full periods. And go ahead and fill in the vertical asymptotes and x-intercepts, please. Okay, so I chose for vertical asymptotes, I chose pi as my first one, and they are 2 pi apart. The vertical asymptotes are, for tangent, are always 1 full period apart. And for my x-intercepts, I chose 0 to start with, and the next x-intercept is 2 pi away. So that's how I ended up with 2 pi n. There are other answers you can write here. If you ever have an alternate answer and you want to check it with me, just ask that question in the Google Doc, or if it's after hours, send me an email. All right. And that's it for today's lesson. And I'll make sure you get some practice doing this sometime in the next couple days. Thanks, guys.